Works.
Yeah, so I'm ready. I can start anytime.
Stacy, the YouTube live starts.
Mhm.
So can we start now?
We can.
Hello everyone, and welcome to our USACO January 2026 contest solution session. I'm thrilled to see many of you here today, fresh up the excitement of the first USACO contest season of the year. Whether you are celebrating a breakthrough performance or analyzing where you can perform, you improve, you are in absolutely the right place. My name is Stacy, and I'm very proud to represent SCAM as we bring you this exciting live session. For those who may not know us, SCAM is a Silicon Valley-based institute dedicated to help middle and high schooler master the art and science of competitive programming. As of 2025, 75 SCAM students have made it to Platinum, and an incredible 41 have been selected for US and Canada camp. Just last season, we had 14 students reach camp, and 3 camp students earned spots in the US national team. Speaking of championships, today we have an absolute legend join us. Camille is an ICPC World finalist, an IOI 2025 problem writer, and a coach who has guided multiple students to gold medals at both ICPC and IOI. His insights into competitive programming are as deep as they come, and we're incredibly fortunate to have him walk us through today's contest problems across the bronze division. So let's get ready for some brilliant problem solving, expert strategies, and the kind of insight that can only come from someone who's been at the absolute pinnacle of competitive programming. Let's give a huge welcome to Camille.
Yeah. Thank you. And I will share my screen so we could start. All right. You should see my screen with the summary of bronze problems. So as Stacy said, I'm Kamil, and I will talk about bronze and silver problems today. Tomorrow, same time, we will do gold and platinum division. Sadly, USACO has not posted the statements on their website yet after the contest ended, but I have the screenshots, so this is what we will work with. Yeah. There were 3 bronze problems, chip exchange, cow splits, and photoshoot. So maybe question to all of you watching right now is, what do you think about the difficulty of B1, 2 versus 3? What was the order of difficulties, and whether you think that it's unusually difficult or not? In my opinion, this weekend, bronze was maybe slightly more difficult than usual, and silver was actually easier than usual. And regarding the problem difficulties, for me, actually Photoshoot was easiest. So for me, but it's not something that is, objective. For me, I would say that problem 3 was easier than problem 1 and then problem 2 maybe. But I'm guessing that for majority of people it will be different, where problem 3 is maybe most scary. If you have some opinion, you can say, or you can write in the chat. Today, after every problem and also at the end of this first hour, so we have 1 hour for bronze and 1 hour for silver. There will be some extra time for questions if you have any. I will make sure to open the chat just in case. So this is my ordering. And as always, I would say that during a contest, you shouldn't focus too much on single problem. You should make sure to read all of them. Even you can do it at the beginning of the contest if it doesn't overwhelm you to think or maybe remember something about 3 problems. But in Olympiads, when it's not guaranteed what is the order of difficulties, you don't want to spend half a contest on the hardest problem. And here I think it's very easy to read the chip exchange problem and spend then 3 or 4 hours just on this problem and figuring out some casework. you don't want to do it. So either read at least two problems immediately, or give yourself some kind of limit that you will, after 1 hour, at least read another problem, I would say. That's just some general advice for the contest. We will discuss at least the bronze problems in order, 1, 2, 3, because it's not really, again, objective that this was just my ordering of difficulties. The first task trip exchange was something about math. Mostly, it's hard to say what category it is. We have Bessie already has some number of chips of first type and second type. She wants to have some number of chips of the first type, and there is exchange rate. Some count we can change from type B into type A. The question is, in the worst case scenario, what is the smallest number of extra chips we get before Bessie for sure is able to get the required number of A chips. And there were some examples. I think it's good to first use something simpler than this, maybe bigger values around 10, just to see roughly what the statement is about. Because after reading it first time, it's not clear what exactly we're doing. So initially, we maybe have, let's say, that number of chips of type A and that number of chips of type B. And then there is some exchange rate, for example, 5B, or maybe let's say 6B, you can change into nine chips of type A. And there is a requirement. Required is that number of A at the end is at least, say, 100. Those 5 numbers are present in the input. And sometimes already with this input, we for sure can get the required number of A chips. Usually that's not the case. And the question is, how many extra chips we need to get before we can achieve this at least required threshold? And we care about the worst case, even though the statement doesn't exactly specify it, it's maybe tricky to understand, at least on this level. Arguably, these bronze division problems, I would say that they were difficult to understand for beginners. It's even about the problem authors and contest organizers that I think arguably they should try to make low division problems easier to understand, especially the problem about squared strings. It used some complicated terminology. Okay, but here, if this is what we know, then let's start working with that before we even try to come up with the full algorithm. If we have this exchange rate and otherwise the B chips are useless, other than just using it this way, then the very first thing we can do is exchange the available B chips into A using this exchange rate. If I have 20, so if I have 20, and every 6 I can change into 9 chips of type A, then how many times I can do this operation? I can do it 3 times, because 20 divided by 6 is equal to 3, rounded down. We here round down. So 3 times we can repeat this operation, and 3 times we will get the 9 chips of type A. Eventually, we will turn this into code. But 37 plus 3 times 9 is equal to this. So actually, that many chips of type A we have. And of type B, after we do those 3 exchanges, so we had 20. 3 times we subtract 6, we will be left with 2. 20 minus 3 times 6, that many of type B. And we can keep working from here. Another thing that is an optional next step, though not necessary, is that if we're talking about the worst case scenario, then for the B chips, I can say that if I add 3 more, so from 2, if I change it up to 5, if I make it 5 chips of type B, it doesn't change anything. So optionally, we should automatically do it because this is the bad scenario for us. We get 3 chips, and actually we don't gain anything from that in terms of the A chips. So let's keep that in mind. This is, let's say, optional step. Okay, what then? I certainly, if I get a lot of chips of type A, I know what is the answer. I mean, 36. If I have that many and I want 100, then extra 36 is enough to reach 100. But we might be getting some chips of type B. And also it's possible that our math, some formulas will give us negative values if the number of chips of type A we have is already bigger than the required amount. If I want 100 and I currently have 164, then I already should say 0. I need 0 extra chips. So that is some step needed. Again, we will eventually make code out of this. So if already A is greater than the required A, then the answer is 0. Answer 0. And we can stop the program. Otherwise, we need to see if what happens if we get a lot of B chips, a lot of A chips, or some combination of that. How many B chips are required before we reach the threshold of how many A's are necessary? B will automatically be changed into A. And if we, for example, have this exchange rate, then 6B is exchanged into 9A, 12B into 18A, and so on. And how many A do I need to reach the required threshold? If I need 100 and I right now have 64, then I can compute the difference, the missing difference, and that's in this case 36. And I can compute how many B exactly is needed to reach that many A. In this case, it's very nice to compute because 24B is required to get 36A. So if I get that many, I'm done. Just looking if there are questions. I don't see any. But this might be not so nice. What if I have, for example, 66 right now of type A? Missing amount is 34. And then I still need that many things of type B before I get enough of type A. So I need to, this difference of what is required minus what I have, I will maybe do it this way, required minus what I have, I need to divide by the exchange rate, which is CA. I think it was like that in the problem statement. Yes, CA.
Okay.
Yes, CA, I think. We're talking about the chips of type A. And we need to here round up. So ceiling. And you might know already that the way to do ceiling is like so. You don't want to use real values, by the way, in such problem. You only want to use integers. Okay, so this is how many times we need to do the exchange. And that many times, then once you compute this, if you now multiply it by CB, which is how many B chips is needed for a single exchange, it is how many B chips are required to achieve this. Okay, so this is one possibility. Another possibility is just simply what is required minus what we have. So required minus have. So this is option one, and then option two. There are two options, and we need to consider the worst of them because the statement tells us to investigate how many chips guarantee, no matter what type of chips we get. So those two are needed to consider. And finally, at some point, we need one more thing. When we keep getting the B chips, so for example, those that we will exchange into 36A, actually, there is one more step needed. If I have that many A, maybe I will bold and highlight it in some way. I have that many A, so that many are missing. And I figured out this exchange rate. Then just before that happens, just before I get the last chip of type B, I can also get some chips of type A, and this will not put me over 100. So this is slightly worst case scenario for me. That is, if to 66A somebody gives me plus 1A, Still, it doesn't change anything about this exchange and how much B is needed. So I can do here plus a little bit of A extra, and that still means that I need all the 24B. How much A can I add? Well, I don't want to reach the previous threshold. So I can also do this kind of exchange. Still, I'm working just on this example of 6B into 9A. If we look in here, then if 27A is missing, then I can do it cheaper using the B chips. So because of that, I want the missing amount to be at least 28. If I increase 66 up to such amount that 28 is missing, so actually I should increase 66 up to 28 is missing, so 72. So if I add 6 chips of type A, it is kind of useless for me, and that's good because we are investigating worst case scenario. And then still, that many Bs changed into 27 As is not enough because I will have 99 As. So I need 24 Bs. Okay, all this analysis, it was without any code. And then to actually solve the problem, I think maybe we can use binary search, though I don't know details of such solution. But whenever it says that we need to determine the smallest possible integer x such that something, then binary search should be considered. And I'm able to believe that there are some correct solutions that use binary search. Maybe, I don't know. My solution is constant time per test case. What I have, I think, is now, it will be easiest for me to just show you the code. I don't have code for all the problems, but I have for some, and especially in lower divisions like bronze, I think it is very beneficial to also see the code versus when you get to, for example, platinum. During such solution analysis, code walkthrough would take sometimes half an hour, and then it's not viable. Let's see, I want chip.cpp. Okay, so this is my code. I read the input, then. One more thing that I didn't discuss and I didn't do in my code is I didn't compare CA versus CB, which again, I think it makes sense. So what makes sense, but I didn't do it, first of all, is binary search. If you did it and you got accepted, great. Second is comparing CA versus CB. Maybe based on that, you know which option you need to go into. I thought that it doesn't matter because I will consider both options and output the maximum. Okay, back to the code. First step, exchange what you have. If you have B chips and you have this exchange rate, then when you divide and you take floor automatically in C++ or in Python, you know how many times you can exchange anyway, or BESI will exchange. And that many times you subtract CB from B and you add CA to A. The asserts in my code, they are some, treat this as a comment. If you don't know what assert does in C++, it's a comment that now I expect B to be smaller than CB. So if I know that I change 6B into 9A, I expect B after this operation to be smaller than 6. If all full 6s I exchanged, then I have less than 6 now. Such assert, they sometimes make it easier to read the code. If you keep working on the code, you can look back and see your comment. It's actually a function that runs and makes sure that this is correct. Once you look up at your code and you see this, you know that maybe some cases are impossible. I think this is nice to have. Then, if we already have enough, so if number A is greater than or equal to the required A, then we need 0 extra chips, we're done. Otherwise, I compute the difference. So I subtract, if I need 20 but I have 10, then the difference is 10, and this is how much extra I need. Now I even wrote a comment that I don't need to take care of A anymore. I just have required A, which is the difference. So from now on, A variable doesn't matter. Okay, what next? Waste B. This is what I discussed where if exchange rate looks like this, and right now B is equal to 2, I can add 3 more chips B, and still it will not be enough to do the full exchange. So I compute this waste amount of how much B extra is wasted, so I need to consider it, which is like here, 6 minus 1 minus 2, CB minus 1 minus B. Now we even forget about B. Oh yeah, because we assume that B, we increase up to the value B minus 1. Okay. Now, the first possibility, the first possible answer is that it's just waste B plus how much is missing in A. Like I told you, if A right now is 64 and required A is 100, then possible answer is 36. After that many extra chips, we have a solution. To that we add the wasted amount of B. And then there is more complicated case of what if we consider using the exchange, using the operation mentioned. And here, I compute the waste amount of A. This is the thing I talked last about. It was here where I explained how from 66, if we increase up to 72, we still don't have enough to make the exchanges easier. There is some math behind that. I will now not go into every single line because then you will be overwhelmed with formulas. Then if you compute here that you need 4 extra chips of type A, then you subtract that for how much extra is needed. Then you divide using ceiling of how much A is needed. You divide by CA, the exchange rate. And again, this is ceiling, so you round up. For some reason, I maximized this with 1. I guess I was worried about the case that I don't think this can be negative. So I was worried about the case when it is 0. Maybe even it didn't work. I think my code maybe didn't work without that maximum with 1. We would need to analyze specifically what happens if now this is divisible by that. And what is the answer? I mean, second possible answer. So this is option 2. It's this waste amount of A plus how many times I need the exchange multiplied by the exchange rate of B. So this is how many chips of type B I have. And for me, it was easier here not to use waste B, but instead just say, if I have B chips and I need that many to succeed, then the difference is how many chips of type B I add, plus how many chips of type A I add. And the answer is maximum of the 2 options. Everything is, of course, constant time. That was the first problem, chip exchange. Time for questions if you have any. And no, I'm not using Sublime Text. This is Genie editor. Also, I can tell you that I'm not a fan of this problem, chip exchange. I think that it's annoying, a lot of casework, ifs. So, yeah, you can say it's math, but it's not actually that you're multiplying something complicated that you need to know formulas. And it's very easy to make mistakes. So I'm not a fan of this problem, but of course it's one of the skills you need to have, to know some basic math and to fix your code if there are issues. In particular, even maybe it's beneficial to know how to write a brute force and do stress testing of your solution. But the best strategy here is just not to make mistakes. Then you will save a lot of time. And that's, of course, very difficult sometimes. We will move on now to the second problem. Second problem, B2, is called cow splits. And for me, when I read all the 3 problems, it is what I left for the last because it seemed most scary to me. I don't know. We have a string given, which is concatenation of the word cow, possibly rotated, or it's a cyclic shift of it. So we have cow, auk, and uko available. This, and that. And we add it, we concatenate it and glue together. Like maybe after this we have another occurrence, maybe then this one, and so on. We are given such a string. Then we choose a subsequence. And as I told you at the beginning today, some problems in bronze today were very difficult to understand, even to read. That's some, I think, bad quality of this bronze contest. So you remove a subsequence. So you choose a subsequence. Let me mark something. Yeah, maybe you choose this character, this one, and this one, and this is your subsequence, CWWO. This one actually wouldn't be legal because it needs to be a square string. Square string is defined a moment earlier in this paragraph. It says that it needs to be some string repeated. For example, this subsequence that I marked here is not good. So it needs to be instead something like CW and then again CW. This is good subsequence that we can erase. So in one operation, we can erase this, and that. Always, of course, even number of characters. We need to transform S into empty string. So we need to keep removing some subsequence until the string is empty. And we need to output what is optimal way to do it, so minimum number of operations. And there is this extra complicated thing which says that in some tests, you don't need to be optimal. You can do one extra operation. That's, I would say, unusual, but in Olympiads often you will get partial points based on exactly the number of operations used. So maybe more common would be that if it's optimal to use 7 operations and you instead used maybe, I don't know, 12 operations, then we take the ratio 7/12, and this is the ratio of points that you get. 7 out of 12 is equal that much, so 58% of points you would get for such test. This is maybe more common, but here it's just this binary thing of in some tests you need to be optimal, in some almost optimal. And it was maybe unusual that K was up to 1. That part was suspicious, and you can even take some guesses of what is optimal from this. Sometimes subtask is also a hint towards a full problem. And then there were examples. A very experienced participant from such subtask and from those examples would already take a guess. And for me, this was my first guess, but I understand that for beginners, it's hard to get this kind of intuition. My first guess, without any reason, without any understanding of samples and so on, is that the answer will be at most 3 operations. Even stronger guess is correct, but this was my guess based on what I saw in sample outputs, that we never here see values bigger than that. And also based on the fact that this is bronze division, where the problems are not supposed to be very difficult. So maybe some very simple construction, very simple operations are always possible. Another thing that suggested this to me is that in some way, the problem must be simpler if we are allowed 1 extra operation. Usually, when, for example, it's some kind of, I don't know, DP problem, if it's dynamic programming and you're computing that the number of operations required is 70, is it that different to achieve something in 70 versus 71 moves? Usually not. But it does make a huge difference whether you do something in 2 or 3 moves. So from both of those, strong, experienced participants would immediately get this guess. And for not that experienced participants, you just need to work more on the tests before you realize that. Now, without even guessing, if we start thinking about it, we will realize the following. The easiest possible square strings are just something that consists of a single character, like this. This is a good string that you can erase. So if there is here, let me maybe make, I will take this. I will make it bigger. Sorry about the quality. What I can do is I can take www and I can erase it. That's one operation. Then I can take all the occurrences of C. I can erase it. And finally take all occurrences of O and also erase it. So even without, it turned out that my guess, my intuition wasn't that useful because in a minute or few minutes you can get this simplest possible strategy. So achieving 3 operations is trivial. You just erase all occurrences of a single character at a time. This is sometimes impossible. You will even in samples see that the answer might be -1. And that's it's clear to see it once you analyze, for example, this thing. You cannot erase 3 occurrences of W because it's not a square string. A square string needs to be string then repeated. So it needs to be even. The parity needs to be divisible by 2. You cannot erase 3 occurrences of W. And generally, if n is odd, then the answer is -1. If n is even, then also the full length 3 times n is even, and then we can achieve 3 operations. Okay, but maybe 1 operation is possible, or 2 operations are possible, or 3 operations. We know that this is possible. So that part is done. We need to figure out if 1 is possible and 2 is possible. 1 turns out also very simple. 1 operation means that at the same time we erase everything. For that, we just need to check if we can erase everything, that is, first half of the given string is equal to the second half of the given string. You can achieve that by using for loop or substring operation. Loop or substring. Whether you use C++ or Python, in both substring function exists, where you check if first half of indices is equal to the second half, or use a for loop for that. If so, then we know that 1 operation is possible. And the only missing part is if 2 operations are possible. That will be the hardest part of the task. But if we can make a mistake by 1, so if k is equal to 1 in the input, which means that we can make a mistake by 1, if it's possible to do 2 operations, we still can do 3. So the following pseudocode is good for k equals 1 pseudocode. If string of 0 to half is equal to string from half to the end, then print 1. And else print 3. It's more Python than pseudocode, this thing. Else print 3. And we need to also output the operations that we're doing. It said that for every character or every index, we need to output in which operation it is being printed, which is non-trivial here. But what we need to do here is for every index, for every every character, we need to output when we erase it. And we can, for example, say that C we erase first, then O, then W, which means that if we see character C, we output 1. If O, then we output 2. If W, we output 3. And well, here we just output 1 all the time. N times print 1. That's the pseudocode solving that subtask mentioned at the bottom of the problem. The subtask worth not maybe many points. It was just 2 tests out of 14. So like more than 10% of the points for this problem. Well, still something. And we have some missing part. Back to the strategy of Olympiad competitions is that unlike code forces or ICPC, implementing subtasks or brute forces, some slower solutions, is extra beneficial in Olympiads because you get feedback and you will get information if so far your solution is correct. So if you suspect that this is anywhere part of the intended solution and just one extra part is missing, then you need to implement it anyway in the full intended solution. So it's not a waste of time to implement it and submit just this part, get confirmation that some tests are passing, and you can safely assume, no, this is correct, I need to focus on the missing part. Versus if you implement everything at the same time, it's then if you have a bug, it's harder to figure out where it is, the bug. Okay, so what about detecting if two operations are possible? There is one part of the statement that we have not used yet, and I would say that it was the most unusual part. That the string in the input isn't just some arbitrary string, because instead it's concatenation of cows, in particular, so just concatenation of those three things possible. Not even just any permutation of the three characters, just those cyclic shifts. It needs to be special in some way. And if you start experimenting with small tests, maybe, like cow with auk, let's say, can we achieve two operations on this concatenation? You will realize that, yes, we can. There are a few ways sometimes to do it. But here I can take, let's see, can I erase first the two W's? So can I erase those two? No, because the remaining part, COOC, is not good. It's not, like, Coco would be good, but this is not good. What else can I do? W can be combined with O, because O is earlier. So can I erase that thing? Yes, we can erase OO. This is repeated string. And then the C with C automatically is done. If you experiment with two strings concatenated like that, you will realize that two operations are always possible. So what if I add something? If I here add another maybe oak and then maybe co, just something random. Of course, I cannot achieve the result using three strings because of the parity. N is odd, then there is no solution. What now? Again, I can try. WW didn't work before, but OW worked. OW, OW. There's also OW here, but then it's not present here, so I cannot do anything about it. If I want the first half to be equal to the second half, then maybe I should leave this OW equal to this OW, and then take something from here that is the same in this part. Right? The property of square, just like palindromes, are often about looking in the middle and saying that this part is equal to this part. That's the nature of palindromes. Versus here, we want to say that the beginning is equal to what is just after the half. And the statement doesn't tell us that the half will be exactly in the middle of the initial string. Half needs to be in the middle of our subsequence. But this is the easiest assumption, that it will still be the middle. So if we take here OW, here OW, can we take from here something the same as here? We already said that for two strings it's always possible. In this case, let's say WC, yeah, WC, 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 and then OW, OW. Right, that's it. I highlighted or I underscored in yellow the subsequence that I can take. And it is equal to OWWC, OWWC. This part is repeated, so it's a good squared string. Remaining part, CO, CO. Actually, automatically, if what you take from one string is the same as in the other, and it's two characters, then the third remaining character needs to be also matching. And it turns out that this is always possible. If you have some free characters, one, so 1 to 3, 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 what you should do, and the full solution is, you imagine the split in the middle, you look at the first three characters and the first three characters after the half, you look at two characters that are the same, in the same order, like here above we took OW and OW. You say that this is what you take. This will give you some characters. So maybe you're erasing those two and those two. Automatically, the third one missing needs to be the same. So in the second operation that we are doing, we will be good. And then you also compare those three and those three, and so on. Using the input here, let's see. There was here some input. Again, sorry about the quality. It consists of a lot of triples. The splits are here, there, here, here, here. In particular, it's very important that the half is exactly there. And what we are doing in the algorithm is the first three characters we compare with the first three after the half, COW versus OWC. We always can choose two characters that are the same in the same order. Here it's OW and OW. Just for every pair of possible strings, you can figure out what to do exactly. And then you do the same for the next pair of triples, cow versus oak. Again, OW is good. Finally, OWC, OWC. Here you could take all three, but I think for safety, let's do the same principle, WC versus WC. This is what I output as my first operation, and the remaining indices are automatically done in the second operation. And that's the full solution, that you need to check if one operation is enough. So if this, maybe let me scroll back here. Oh, I'm here. Okay. So now full solution is that first we check if one operation is possible. So first half equals second half, and else always two operations are possible. So you output 2. And here you make a for loop. Let's say you iterate the first half of the characters for I equals 0, and then you keep jumping by +3. In C++, it would look like this, smaller than half, and I plus equal 3. So this way you iterate the first half using triples. You jump by 3. And here you compare S of I plus 1, S of I plus 2. So this is this triple here. And you also look at S of I plus half, I plus half plus 1, I plus half plus 2. You have this pair of triples, and you now need some ifs to see what two characters are the same in the same order. Maybe, for example, the first character is the same as this one, and then second character is the same as here, third one. If so, for those indices, we output 1, and for others, we output 2. We don't actually output right here, we have some extra helper array. And what we do here is we say then answer of I equals answer of I plus 1 equals answer of I plus half plus equals this equals 1. And other things we mark as 2. It might be scary thinking about those cases. Certainly, we don't want to look at 3 possible strings and then all 9 possible pairings. We don't want to make ifs for. If we quickly look at my code, what was the name? Was it splits? Yes, it was splits. In my code for this part, if n is the length of the full string, then I have this for loop over the first half. I keep jumping by +3. And I do the following. I check if the first character Si is equal to which of those other three, and it automatically implies the full comparison because we don't have that many possibilities of the orders. Remember, just cow, oak, and what else? WCO. Those are possible. So if I know that in one triple I have C something something, in the other I have C something something, everything is the same. It's cow cow. If in the first I have cow and in the second I have something C something, I know that those two are equal to those two. So even in my drawings, I told you that there are too many cases. It's not that bad. So I just check which relative shift it is. There are three possibilities. And depending on that, there is another, let's say, pair of indices that I need to say for those operations, I'm doing them in second operation. By default, I created array with only ones inside. I have a vector with n elements equal to 1, saying everything by default I'm doing in the first operation. And then some things I do in second operation. And then the code turns out very simple. If you have any questions, then now is the time. The time complexity here is just linear. We don't have any nested for loops, so it's O of n. And that is the end of the second problem, which is cow splits. Half a minute more for questions, then we will move to the third problem, Photoshoot. Let's do the third problem. In Photoshoot, we have a grid of size n by n, 500 by 500. And inside, we investigate what square of size k by k I should choose. So where is the optimal one? So that we would maximize the sum of numbers inside. There are updates every time the number in a single cell increases by positive integer. So maybe this square was the best, but here there was value, say 7 somewhere here, but now 7 changes into 20, and because of that, maybe now there is new optimal square. So values keep growing in the grid. After every update, every modification of number changes into something bigger, we need to output what is the maximum possible sum of values inside of k by k square. Turns out that in this problem, it doesn't help to be a very strong participant because you might overkill this problem. You might do something very complicated. If you are, let's say, silver gold division, many people after reading this will start thinking about complicated two-dimensional data structures. Namely, if you want to have maximum in two-dimensional grid, something called two-dimensional segment tree might help with that. And I think it's a valid solution, but just very complicated one. Also, it will do log squared per operation. Once you learn this data structure, and in bronze, you don't even need to know what it is. Even once you learn it, you can quite safely assume that you will never use it anyway, because Olympiad problems extremely rarely have this as the intended solution. So it's more of a warning towards those of you who already know complicated data structure. Don't try to use it. In my life, and I solved thousands of problems, I used this thing maybe once. So it's very rare. Sometimes it is alternative solution, but basically never it's the intended solution. Just ugly, complicated, and slow data structure. We don't want it. So I'm not going to discuss the exact solution using it. Okay. When they are talking about 2D rectangle or grid, and we investigate sum of subrectangle, you should certainly consider 2D prefix sums. And if you don't know what that is, then certainly you should learn it if you want to get to silver division. But there is a strong reason why prefix sums will not be useful here. Actually, let me ask you, maybe somebody can tell me a reason. So do you know why not 2D prefix sums? When we have this problem that there is a grid, we are looking for maximum k by k square, and there are updates that increase some single value. Why it doesn't make sense to consider this too much? So if you get the idea, you should discard it. Why? Any ideas? The answer is that because there are updates. Because of updates. 2D, generally, even not two-dimensional. Prefix sums are a static structure. This makes sense for an array that doesn't change. If you are given one array, it doesn't change, and you have some things, some queries about ranges, the sum of a range, or sum of rectangle in 2 dimensions, then 2D prefix sums are reasonable to consider. Very often it's part of the intended solution. But if there are updates, then this is not viable. Unless we are getting into segment-free territory. So this is why that's not a solution. We will not do it. Instead, what I very briefly showed you already is some kind of a hint where 7 I changed into 20, and I said that because of that maybe the square will be in different place. Another hint is in the statement that one of the constraints is very unusual. K is up to 25, the size of this square, which suggests that we will iterate such square. We will have for loop of size 25. Also, Q is less than usual, 30,000. So from this, we could already take a guess that the time complexity is Q multiplied by K, or maybe even K squared. That, if you compute, will be maybe 50 million operations or so, which is okay. And even time complexity here is, I think, a nice hint, and it can tell you what is the intended solution. But back to this thing that I told you, it's a hint. If at some point the optimal square is somewhere, and you know that its sum is equal to something, sum equals, let's say, 300. If somewhere else in the grid value 7 changes into value 20, so now this is new updated value, it doesn't make sense to consider the square to now be in all the random places in the grid. Those things didn't change, their sums didn't change. So still here the sum is equal to 300, or maybe a square containing this value 20, so one of those few squares here, is better now. You only need to consider squares that contain the value that has just increased. And the number of such squares is k squared at most, 25 squared, because it needs to be nearby. The row is one of the previous 25 rows, and the column is one of the previous 25 columns. The top left corner of such square will be somewhere here, in one of those places. This is where the top left corner of a k by k square can be, so that the square would contain the value 20. So if you knew prefix sums and you wanted to use it, it seems that if they tell us that the value RC changes into something new, let's say it was 7, now changes to 20, you might be tempted to say that now we iterate the square, so top left corners nearby. So for something in range from r minus k plus 1 to R, for j in c minus k up to c. We here iterate the top left corner of a square that contains me. And now I consider this square, so everything from a of r ij of size k, and such square of size k, with prefix sums, you could query in constant time what is the sum. But we cannot do it because of updates. Still, I want here in constant time to know the sum here. But if I know that this thing changes from 7 to 20, then I know that the sum increases by precisely 13. 7 to 20, the difference is 13. So what I can do is I can maintain the sum for every position. For every possible top left corner or every cell, I keep the sum of a square starting here. And what I will do here is the sum starting at this position, I will increase by 13 by the difference new minus old value. And this sum is now equal to something. It only could increase. And the answer maximize with this new sum. This is what you need to do when you have an update. And after that, the variable answer, one global variable, contains the new answer. Possibly it got updated up. So you do this for a query, and just after that, you output the answer. The only here tricky thing is maybe to make sure that in those for loops, you're not moving out of bounds. I will very briefly show you my code, but I don't think it's worth discussing. Photoshoot, it's just this. I have, why do you have old value? I guess for me, array A is the sum, and old value is the elements of the grid. Then after reading the query or the update, I iterate the for loop, the backwards things. What is the top left corner? So the previous k rows and columns. And the sum starting there, I increase by the difference new value minus old value, and I maximize the answer. It's that simple. Time complexity is q times k, qk squared, as I mentioned at the beginning. No data structures needed, no prefix sums. Just the main idea is that we keep at every position, every starting position, we keep the sum of values in a square starting here. This is indeed the easiest one. I would say so. For me, it was easiest. Also, for the first problem, it's easy to get some idea, but then getting all the details right was difficult. Okay, time for questions, both about this problem or about the bronze contest in general. After the questions, we will move to the analysis of silver problems. And tomorrow we will do gold and platinum. And while you think about questions, I will go grab water for myself. Okay, silver problems. The three problems were lineup queries, Mooclear Reactor, and sliding window summation. Maybe again, let's start by discussing the difficulty, in my subjective opinion. What was linear queries about? Okay, I will say this. Without computer, without running a program, I would say that, so without computer, just using paper to solve, I would say that S1 is very hard. And what about S2, S3? I think S3 is easiest, then S2, then S1. That being said, S2 has this property that if you're experienced, then you already have seen similar problems, and this one isn't really new. So for me, S2 didn't really have a step that I didn't see before. Because of that, it was relatively easy. Then with a computer, I think that S1 becomes easier because you can run a program and see a pattern. So with a computer, if you are allowed to run a program and see what it says, then this drops down maybe here. But if you have a different opinion, I will gladly hear it. I see a question for the second problem. I thought you could cancel multiple subsequences. Yeah, you cancel one at a time, but it shouldn't matter if it's at a time or separately. But yeah, you split this in that previous problem, you split the string into a few subsequences. It doesn't matter the order of them. So I'm not sure about your misunderstanding of the statement. It seems equivalent. Maybe you have some bug. Okay, then that's my opinion. But we will do things in order. Again, I don't think the difference of difficulty was that big, so it will be easier and less chaotic to just go 1, 2, 3. Again, like I said at the beginning of bronze, you shouldn't, during a contest, open one problem and keep working on it until the end of the contest. That's not optimal. You should either read all the problems, or at least two, or you should, after some time of thinking on one, switch to another. Unless you're already experienced and you know when you see an easy problem. If you're not on level of higher divisions, then it's just dangerous to be stuck on one task. Okay, lineup queries. There is a line of cows. I think it will be easiest if I explain it by also simulating. Initially, there is cow number 0 on 0th position. Then there will cow 1 will come. And then what happens at time 2? They said that at time 2, the cow at position 0 moves to position t over 2. So moves from position 0 to 1. So what will happen is the cow 0 will move to position 1, so those two will swap. And then cow 2 joins at the end. What happens next? Again, from here, at time 3, so now t is 3, cow at position 0 will move to this divided by 2, which is 1. So this guy will move here. 0, 1, 2, and 3 will join. Then time is 4. The first cow moves to position this divided by 2. So position 2, which is here. Those cows will shift to the left. 1, 2, 0, 3. And 4 joins. And so on. That's what happens. And simulating this on piece of paper is very time consuming. It was convenient that organizers provided the simulation of the first 10 turns from 0 to 9. But what is even more convenient is that in few minutes you can implement this thing yourself. And this is what I did when I wanted to solve this problem. So we can implement and just output the first 50 turns. And then there are queries of two types. One is, say, and the constraints are up to 10 to the power 18. So you need to be very fast. You cannot simulate, at least not for the full score. Given some cow ID, where she is at some time, and at position X, at some index at this time, which cow is there. But instead of thinking about those things, let's just see this process and try to observe a pattern. Because on paper, doing such problems is difficult. Maybe eventually you can get proper observations, but why not use a program? The name of this was lineup. Lineup indeed. Okay, I'm going to. So I used C++ vector for this, and yeah, I didn't do anything fancy here. Let's first print it this normal way. Too many arguments, percent. Lineup. Okay. If you just print it in your console like this, you can get some ugly formatting, especially if the line is too short. What I strongly recommend is saving it to a file. So I'm going to run the program, but save the output to a file. Then in this file, this is what I see. I will increase the font. So this is what happens after turn number 4, after 5, and so on, and we can keep scrolling and we can observe patterns. Another thing that is a small preference of mine is that eventually it's difficult to see indices because some digits are 2-digit long, some numbers are 2-digit long, some are 1-digit long. In C++, if you use print, there is this nice trick of %2d to say that every number you want of this length, of length 2. And C++ will automatically put extra spaces. You can also try %02 to make it pad with zeros, to do extra zeros at the beginning, leading zeros. But I'm going to do it this way. And after that, like, it's not a big difference, but now everything is nicely lined up. Maybe still it's hard to understand looking at a lot of numbers, but I know this number is above this number, so they are at the same position. Every single digit number got an extra space at the beginning. Even if you didn't know the command, then you could achieve that with an if. If x is smaller than 10, then output an extra space. This is pseudocode, but this would achieve the same thing of lining up the numbers so that the output would be easier to analyze. Okay, first thing I tried is I looked at every row and I tried to understand the pattern. 3, 5, 2, 0, 6, 4, 1. I don't see a pattern. Sometimes it relies on binary representation of a number, especially when we use division by 2, for example. If 0 is at the beginning, then maybe on the left we have odd numbers and then even numbers. We are looking for stuff like that. Sadly, no. Just looking at a single row, I couldn't observe a pattern that would be useful. But if we look at some particular number, or if we look at columns, then we will see patterns. Look at where the value 6 is. Value 6 is here. So at time 6, the cow 6 gets to the end of the line. Then she's at the same slot, same position, until she reaches, until she becomes a cow in the middle of the line. And then other cows start jumping over it. Something from the start moves after the 6. So if you look at where 6 is, it is at the same position, which is position 6. And eventually, she keeps moving to the left by 1, from position 6 to position 5, 4, and so on. And after 0, she jumps to half of the line. Then keep moving slowly there, and so on. So for the first 5 turns, cow number 6 doesn't exist. For the next roughly 6 turns, she exists at position 6. Then it's position 6, 5, 4, 3, 2, 1. After that, she jumps to the current half of the sequence. And if you do the math, it is around position 9, I think. Because this was moment 6, this is moment 12, this is moment 18. Half of 18, the middle is at roughly 9. Then you keep moving there. And after 9, she will be roughly at 9 times 1.5. Then this point times 1.5, and so on. Now, I think this is still kind of tricky to see, especially for you, because you're seeing my screen and maybe even the font or quality is messed up. So one more thing that I tried is this trick where I said, if the value is 7, then print 7, else print a dot. If I now run this program, and I can even output maybe 100 lines or more. So I want to now run this, open the file, and now you will see nicely where the number 7 is, and we can keep track of it. If I scroll down, it's very regular how it behaves. You can also do the same for another number, not just 7. So at time 7, the 7 appears at the end. For 7 turns, it is at that position, and then keeps moving very regularly. We can even look at rows to see for how much time that happens. So at row 20, here one row is missing. Well, okay, so row 0 is missing, so it's good. At time 27 is here. At time 21, it resets to half, then gets there. At 32, resets again to the half. At 49, resets again to the half, and so on. Such drawing might even help for your math. And if you're worried about some off by ones, I would look at this drawing and make sure, yeah, after the 7 at 21, which is exactly 7 times 3, resets for the first time. So I find this drawing very useful. And now, does it help us solve the problem? Because we only here analyzed patterns. We didn't even start talking about an algorithm. So how do we solve it? What did we even need to solve? At what position is some cow at some time? And the time is huge. Well, I know that initially the cow doesn't exist. I know that from the cow 7, from time 7 to time 13, it is at this position. So generally cow C doesn't exist initially. Then in the time in range from C to 2 times C minus 1, position is C. And then it's less trivial, but something happens for 7 turns. Then for 7 times 1.5, again, just do the math of if the size here is 14 and you wait for 7 extra turns, then the size is 21. 21 divided by 2 here is this 7. So the position here is 7.7 times 1.5. Rounded up or down, you can look at some example and just see if it's up or down, or look at the statement and see if it's rounded up or down. And then, so this is like, I don't know, 11. Then after 11 more turns, where will we be? Where if this size is 21, 14 times 1.5, after 11 more turns, I'm around 32 size, and half is this. Maybe even instead of keeping the position, keeping track of position, I think it's even better to keep track of the size of the sequence or the time moment when the cow resets to half of the sequence. So I know that the first position when we are in the half is this. So that's 13, right? Not 14. 13. Then we have this reset at 21. We have this reset at 32. Then we have this reset at 49 and so on. 32 times 1.5 is 48. So apparently we even add 1 because of that. You see this example, even without looking at the statement, it sometimes allows me to see that there will be a +1 needed somewhere. I'm not saying that this is extremely safe because it's a single example of investigating where value 7 goes. But from my experience, looking at example to see if +1 is needed is very useful. Just try both parities. I would create second file where I would see what happens with value 8. And if I get 7 and 8 right, there is, I don't know, 90% probability that I get everything right. Okay, and now why is this fast if I keep simulating this, if I keep analyzing? Well, because if you keep multiplying something by 1.5 roughly, you will, in logarithmic number of steps, get 10 to the power 18. The time complexity that we're aiming at is logarithm of t. Where am I here? Logarithm of base 1.5 of t, where t is the time. So this is, I want to move here. This is our target time complexity, logarithm of some base. This base is still a constant factor, so actually, formally, we don't need to type this in time complexity. Logarithm of t is the time complexity of our solution that we will in a moment discuss. And the solution is that we first do this check, and then we keep this single variable of, let's say, size of the sequence when the cow resets. And always, if we know the size, we know this position of the half, and this position of the half is exactly after how many steps we reset again. So the code is roughly that size is this, half is equal to, I think it's that, but you can check the math later. And the new size is just size plus equal half. This size corresponds to the current time. So when you get to the moment when the time from the query is in the range from size to this next size, then you know that this is when the time from the query is. And if right now, let's say the size is 21 and you're querying about the time equal to 25, then you know that from 21 to 25 there are 4 steps. So from this position of half, the cow will move to the left 4 times. So the answer position is half minus time of the query minus the current size. That's what you output. So it turns out quite nice to and easy to implement. Just be careful with off by ones. So this rounding up versus down, either you need to be very careful analyzing the statement or analyze maybe 2 examples of what happens with 7, what happens with 8, and make sure that your code works for both. It's up to you which strategy you take. That's half of the problem. Well, sometimes such half of the problem might be the way easier part or way harder part. We still have separate query to answer. Which cow is at a position X? Whoops. Here we go. Which cow is at position X just after time t? So this time we are not investigating a particular cow, so we cannot track her movement, but instead I'm asking about some random position. Let's say, I know maybe this will be too much work. Or okay, here. I'm asking about something here. Let's put X and let's zoom in. Somebody asked me, at time 34, at position number 8, what cow is here? And I know, either looking at here or this version with numbers printed, that the same cow for sure is here and here. I don't know what cow, but something is there. X, X, until I get to the half. So I know, maybe here there is a half. And after half, either this is the first moment when this cow is here, that is, maybe this is the beginning of this cow. So maybe this cow looked like this. It started here. That will be, in particular here, at time 13, what is at the end is 13. So maybe this is 13. If this is perfectly 13 times 2 minus 1, so 25. If this was row number 25, then the answer here would be 13. But that's not the case. So instead, if this is not that case, what happens is a cow got to this half because just a moment earlier, she was at the beginning. And here we repeat this process. X, 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 X. And when we get to the half, we again check, does the math confirm that whatever is the middle here, it perfectly matches if we look up, whatever starts here, that would be 8, is 8 indeed here. And it's some simple math of 8 times 2 minus 1. Is it equal to 19? No? Then no. If this is indeed the middle, or let's say this is the middle, then you reset. So you do here. And you continue going until you get to the half. Let's say this is the half. And maybe this here, the math will be right, that this is 6, and this is indeed 6. And then you know that what was here is a 6. I don't know exactly. I chose middle every time very roughly. But that's our idea. And again, this number of times that we reset, that we change from the middle to position 0, is logarithmic. Generally, I have a lemma up to time t, every cow resets log of t times. Resets means changes between 0 and half of the sequence. And otherwise, the cow travels very simply by 1 every time, unless it's the prefix of the time when she stays at the initial position. Okay, so roughly what is the algorithm here? We are given the time and the position. We don't know what cow it is. We do some simple math to figure out, looking back, when the cow gets to the middle. So if right now there is some time t and some position p, as I go back in time, I do t minus 1. So I keep doing t minus minus and p plus plus until p is half of t. If you're very lazy and you hate math, you can do binary search for that, to be honest. You can binary search going backwards after what time I cross the middle. But also, I'm sure this can be done with a formula. To be honest, I didn't even write down this formula, but it's doable. So roughly you want t, let's say that after k turns, this will be correct. You want p plus k to be half of this, so you want twice p plus k to be equal to t minus k. 2 times p plus 2 times k is equal to t minus k. 3, if you move k to the left side, 3 times k equals t minus 2 times p. So k is equal t minus twice p divided by 3. And I will say plus minus 1, or actually plus minus a lot. But roughly, this is a formula. If you are given some time and the current position, then after that many turns backwards, you will be in the half. And I here didn't care of plus minus ones. So what is a nice but ugly trick is that if you compute that after that many turns, roughly you are in the half, what actually I will take is I will do here minus 5, just maximize with 0. And I will say this. And this is what I would do during a real contest. I want to immediately jump by that much backwards. So the time t and position p modify by that much. And then keep going by 1. Until you know that you're in the middle, that in the next turn you should reset. This way, you don't care about the off by one errors in this math, in this equation. So what will happen is in constant time from x, I will jump, let's say here to this position. And then I can go 5 steps or so. I can go step by step. It doesn't hurt the runtime. And eventually you will see, oh, this is such position that I got here from 0. And you need some check for that, whether, again, you can look at the full drawing of numbers generated by my first program and see how do we check if given time and position is the reset time. So is it division by 2 rounded up or rounded down? Or again, analyze the statement precisely. So that's how we solve this task. I will not show you the full code because I don't even have it. I've seen in Discord, in the USACO unofficial Discord server, somebody pasted their correct code if you want to find it. Time for questions if you have some. second task is this. Unlike the previous problem, for this one, I think it's very easy for experienced people because they've seen similar problems before. And if you have not seen similar problems, then this one is crazy difficult. When you see this for the first time, I think it's very hard to come up with a solution. But that's part of competitive programming. You need to solve a lot of problems to see a lot of tricks and techniques. We have n rods. Each has some range, safe, stable operating range, and we want to maximize the number of rods that are within their accepted range. And there are conditions, M constraints of form this, that a pair of rods has a condition that the sum of their values needs to be exactly equal to z, or z. Now, first thing is, you can kind of intuitively maybe even guess from the names of variables, n, m, the m always connects two things, that it is beneficial to think about it as a graph. Also, you can get to this fact if you think about contradictions. If you try to create a small test where it is impossible to assign the values so they would satisfy those equalities, you will see that at least you need three values, 1, 2, 3, and you need some condition about the sum of the first two, those two, and for example, the parity doesn't match. Yeah, the unnecessary but extremely convenient way of thinking about this problem is that it's a graph. And in this graph, I have those rows, so nodes. So I have actually n rows is equal n nodes. Even the name is similar. So let's say we have that many nodes, m edges. And I have the nodes, let's say 1, 2, 3, 4, 5. Then there are edges with information. The sum here is equal to 7. The sum here is equal to 10. The sum here is equal to 3. The sum here is equal to 8, and so on. Already from that, we can detect contradictions. And there is a separate way to think about contradictions. But again, there is a well-known technique that doesn't do it separately and just immediately makes a step towards figuring out the relative values. And that is, if you know what is the sum of those two values, if you know that the sum is 7, if I told you just a single of those values, say here I told you the value here is 6, then you automatically know that the sum here is 1. And because the sum here is 10, you automatically know that the value here is 9. 9 plus 6 is equal to 15, so this is contradiction. So this was actually impossible, but I can actually continue my logic. The sum here is 8. 9 plus negative 1, the values could be negative, is also 8. So every value implies neighbors. And instead of thinking about a particular value here, a constant value, I can think about it as a starting variable. So this is a well-known technique that we often perform if we have sum of values. I've seen a lot of similar problems in the past where, for example, maybe even it's not a graph, but there is sequence of values, and let's say you are given the average, the arithmetic mean of every two consecutive values in an array. So if you instead saw this in the statement, so somebody told you a of 1 plus a of 2 divided by 2 apparently is equal to 7.5. A of 2 plus a of 3 divided by 2 is equal to also something, let's say 20, and so on. The way we solve and analyze and think about this kind of problems is the same. That is, you assume that a of 1 is some kind of variable x, and you see what it implies about other nodes, other variables or unknowns. Also, it's a common way to solve a system of equations, and this is what we have here. So like if I told you x plus y divided by 2 is this, from this you could express y in terms of x. Here y is equal to 15 minus x. But we don't even need to think about this problem. This was some example to help you in the future detect similar problems. Actually, forget about that. If we're here, if I say that the value of node 6 of node 2 is equal to x, then the sum is 7. So what here I have is 7 minus x. If this sum is 10, 10 minus this is equal to 10 minus 7 plus x, x plus 3. If this is 8, then what I have at 5 needs to be 8 minus x minus 3, so 5 minus x. Additionally, I have a condition x plus 3 plus x is equal to 3. So I can write on the side x plus 3 equals 3. From that, by coincidence, x is equal to 0. It doesn't really matter that much that it's 0. It's a coincidence. We just here got unique possibility of value x. Sometimes it's not unique, even if there is cycle in a graph. Let me show you an example of that. I'm guessing that if I put here 20, I put here 17. Then what I will have is, because of the 17, at 1 I need to have 17 minus x. And now if I look at this edge, 17 minus x plus 3 is not very useful because it's always equal to 20. So there is infinite number of solutions here of this graph, even though there is a cycle, because often people will think that if there is a cycle, then there is contradiction or a single solution. Well, not always. Generally, it's a system of equations. And if somebody tells you that there are, let's say, n equations and n variables, there can be many different outcomes what comes from that. There might be 0 solutions, so contradiction. There might be 1 solution. There might be infinite number of solutions. Okay, so you at some node imagine you put a variable x and you can express everything else in terms of x. Actually, every node in this connected component will be either of form x plus constant or minus x plus constant. Those are the only two formats possible, because always if node is in one of those formats, if you look at its edge to some unvisited node, the math will be that if, let's say, I'm x plus 7, the edge is 20, then 20 minus x plus 7, in this case, is equal to minus x plus 13. It always gives you the second of those two formats. Of course, this is separate for every connected component. So if there is another connected component with 6 and 7 and edge between them, maybe edge of value 50, then there is here separate math. There is separate kind of variable x2, let's say. And here maybe there is 50 minus x2. Okay. So that was what I said initially is well known for experienced competitors. And now something specific to this problem is that we are given ranges, operating ranges LR, and we want the values, the unknowns, to be in such a range. So we are rewarded if x, for example, it has some good range where we want it to be. Maybe x we want to be in range from 1 to 5. And maybe in this node, we want this value to be in range from 10 to 20. And sometimes we cannot satisfy both. But because we know that every node needs to be of one of those formats, then the fact that this value 7 minus x is in this range we can express as simple inequalities. Let's see, not sliding window. I think, or maybe I will scroll down. Let's erase this. Either you have something like this, 10 smaller equal than x plus 3 smaller equal 20. This transforms to x in range from 7 to 17. If instead you had the other type of inequality, so 10 smaller equal minus x plus 7 smaller equal 20, maybe let's use 6. Then let's transform this. That highlighted part is equivalent to, if you move x to the left side, then this is equivalent to x smaller equal than 6 minus 10 minus 4. And then this part, you need to move x to the right-hand side. X is greater equal than negative 14. So what we have actually is that, again, it's a range for x. X is in range minus 14 up to minus 4. Turns out that each of those conditions, no matter if the variable in this node we know is equal to 7 minus x, or it's equal to x plus 3, no matter what, every blue range, the desired range from the input, gives us information about the range of x that will be good for us. So what happens is every node says, oh, if x is in range 1, 5, it's good. We get plus 1 to the answer. This also implies if x is in range from minus 14 to minus 4, then plus 1 to the answer, and so on. In a connected component, we get a lot of such information. Every connected component gives us x must be in 1 to 5, x must be in minus 4 to minus 2, x in minus 14 to minus 4, and so on. We often cannot satisfy all those requirements, but what we need to do is choose such integer x to maximize the number of satisfied conditions. Maximize the number of conditions satisfied. And this becomes a standard problem on ranges. And this one, I would expect almost everybody in Silver Division to be able to solve. This is not a difficult problem anymore. The difficult part is done. Solving this, like, most people, I think, will think about it visually, or at least this is what I would do. If you have range from 1 to 5, from minus 4 to minus 2, from minus 14 to minus 4, from 4 to 10, you're looking for such x that most ranges include it. You're looking for such integer position x that you maximize the number of ranges that include this x. And that's done with sweep line, so some kind of sorting. You can also do, I don't know, segment tree, maybe prefix sums, but there are many techniques that can solve this problem, and it's a well-known task in computer science. So just to discuss at least one method, the way I would do it is I would try to iterate or sweep this drawing from left to right. So I would collect every event, every value, like minus 14, minus 4, and so on. So if there are, let's say, n nodes in connected component, then I would collect all 2 times n values or endpoints. I would sort them. So I would have them from left to right. And in this order, I would iterate. At every start, we do plus 1. At every end, we do minus 1. And always the current value, plus 1, minus 1, is the current number of ranges that are active, number of ranges that include the current x. So in this order, you increase something by this plus 1 or minus 1, and you maximize the answer with the current variable. If there is a tie between some endpoint and start point, then you process the start point first, because you want to say that here at this position, this range starts, so this position counts as intersecting 2 ranges, not just one. That's one way to solve it, but I'm rushing through this part because, again, it's the simple part of this solution. The difficult part was here. To summarize the solution to the problem, we read the input, the n nodes with some ranges that we will leave for later, the m edges. We run DFS to find connected components. In every connected component, the first node from which we start DFS, we say that there is some unknown variable x. We express all other nodes as x plus something or minus x plus something. Every node will be in one of those two formats. You can keep this as, for example, an integer and a Boolean variable, false or true, plus or minus. You mark all the nodes, so the DFS will reach all the nodes in this connected component. It will put the formulas there. Always when you see edge to already visited node, you check if there is no contradiction. So you always see if, for example, you have x plus 5 plus x plus 7 needs to be equal to 20. You always look for contradiction and you look for something that implies the value of x perfectly. For example, if you have this, so you have two neighbors with the same sign next to x, then it will give you x uniquely. In this case, twice x plus 12 is equal 20, so 2 times x is equal 8, so x equals 4. So this is unique value of x. Sometimes it will give you contradiction because of parity. For example, here we would have this. 3.5 is illegal, so you would say -1, impossible. If the two neighbors have different signs, like x and minus x, then you will either get contradiction, like here, or you will get no information, like here. This equality is always satisfied, so you don't gain anything. Then, once that's done, either you got a single x and you need to compute how many ranges in the connected component are satisfied, or you have no extra condition on x, then you start looking at the LR ranges. Every node in this connected component you need to transform into a requirement like x needs to be in range from 1 to 5. And then it's a standard task of your given out of ranges, find a value that belongs to most ranges. And that's usually solvable in n log n. That being said, yeah, n log n. So because of that last part, the full thing is n log n or m log n. But everything before that was linear. Finally, the total answer will be the sum of answers from different connected components. Time for questions. I see some strategy question, I guess, unless it's about a particular this problem. How to choose which is the best solution when you have a lot of strategies? How long does it usually take? If you have a lot of different ideas or a lot of different, techniques you can think of, algorithms, and so on, then there is no golden rule about it, about the strategy of order of solving. And because of that, some problems are hard because you just cannot decide because there are many possibilities. Just certainly, I wouldn't recommend trying the first idea that you have and going very deep into it without considering other things. So maybe some reasonable piece of advice that is your problem solving with BFS, not DFS of orders or of ideas. So if you have a problem, let's see here. If you have a problem and you think, oh, maybe binary search, maybe DP, maybe this, maybe that, it's not always a great idea to say, okay, binary search is my first idea, so then I need to sort, then I need to do this, then I need to do this. After it depends on the problem, but let's say after a few minutes of this, if it doesn't seem to be an easy problem solvable this way, you need to also investigate other ideas like dynamic programming. So yeah, BFS is better if you try one idea, another idea, another idea. Then usually you choose the one that seemed more reasonable and you go a little bit deeper there, but still you have in mind those other ideas. In lower divisions, usually you don't need to go that deep into one idea before you see if it's a solution or not. Last problem, sliding window summation. For me, this was the easiest problem in this silver contest. There is unknown hidden binary string, and we are given some information. The information is about windows, so a sliding window. For each of them, we know the parity, the remainder, modulo 2, of the number of ones among the consecutive k bits. Also, in Olympiads, there are subtasks, right? And often, if you're stuck, you should try them. And both today and tomorrow, my plan is to talk about subtasks if it's an important step towards the full solution. Otherwise, I just go towards general observations and then the full solution. Okay. If you have a binary string, especially when we have unknown array, I like to think about it as series of underscores. And we know among consecutive, let's say those four, let's say k equals 4, we have the parity. Equivalently, we know the sum modulo 2 of this range, the sum of bits 0 or 1. Even equivalently, it's XOR. It's not needed to think about bits this way, but while solving this problem, I prefer to think about it as XOR of bits rather than the sum modulo 2. But you do you. Sum is also good. If you know this sum, and then you know the next sum, then you know that both use mostly the same bits, with one exception, the first one and the fifth one. So position 0 and position k. This is the only difference. If somebody tells you that the sum of the green range is something, let's say 0, and the sum of the yellow is 1, then it must mean that whatever bit was here, the one at there, the position k, is different. So this combination of two different pieces of information given about two consecutive ranges, it means that those two bits are different. Versus if both such ranges have the same parity of the sum, or parity of the number of ones, same thing, then it means that those two bits are the same. Because taking those 4 bits gives the same result as taking those 4 bits. Those 3 bits are common, so apparently taking this bit versus taking that bit is the same. So, and then this thing continues with something similar. If you know the sum here of this yellow range, and then we look at this blue one, we have a comparison of this bit versus this one. We know if it's the same or different. If we keep going like that, what we will get is for every bit, we will know if it is the same or different than the bit k positions later. So maybe here we know that it's the same as this position. The green, let's say, means same or equal. Same. Position, always it's position I and position I plus k. And then we have this information, maybe we know that this position versus this one is different. Different. And we have all this information, this pair, this one, this one, this one, and so on. Now, if we just phrase it this way, it's a little bit chaotic. But similarly to the previous problem, we can observe here connected components. If we know the comparison of whether bits are the same or different of those two, we also know if the I plus k is the same as this plus another k. And then from this one, we know if it's the same as yet another plus k and so on. Then this is one connected component. We know if bits at position 0, k, 2 times k, for each consecutive pair, we know if it's the same or different. And if I told you that, or maybe let's use the same technique as in the previous one. If this is bit x, and this is the same, then we know it's also x. If this is different, then we know it's not x. If this is the same as previous, then it's not x. If this is the same as previous, then not x. If this is different than x, and so on, then you will know from this that maybe there are 30 bits equal to x and 25 not x. The task told us that we need to do what? I think maximize minimum and maximum number of ones. Well, okay, for minimum you use 25, for maximum 30. The number of ones. Number of ones. Yeah, that's it. If you want maximum number of ones, then x should be equal to 1, and then 30 things in total are equal to 1, and 25 will be 0. Or the other way around, you can set it to 0, and then this is the number of ones in this connected component, so among those positions. Then you can do the same logic for, for those. So a of 1 plus 2 times k, and so on. Generally, every group of indices with the same remainder modulo k will be one connected component. Okay, and there is one last thing. The thing is that we also, the information about green and red edges, so those comparisons of this versus that, they came from comparison of two consecutive ranges. But nothing we did guarantees that the very first range is correct. So we are given the very first sum modulo 2 of the first k bits. And what this green range, for example, represents is the following. If we know that this has good parity, then by comparing this range versus that one, we figured out what is the parity of the next bit compared to the 0th bit. But still we need to guarantee that this has good parity. Otherwise, what might be happening is by doing this and saying that we minimize or we maximize, we might allow situations where in order to maximize, let's say, the number of bits, this becomes 1, the very first bit, and it implies what is at this position, this position, this position. Then in order to, again, maximize the number of ones in the full string, I put a 0 here, and it implies those positions. Then maybe I put another 0 here, and those positions. And finally, maybe I put a 0 here, and it implies those positions. But maybe in the input, we were given information that this is even. But hey, it's not even. One of those bits needs to be changed into the other possibility. 1 into 0 or 0 into 1. One bit needs to be flipped into the other option. So when we look here at the 30 versus 25, I know that this is the better option for maximizing the number of ones, but I can flip my decision for the cost of -5 to the answer, and then it will be the opposite. So for each of those k first bits, I need to figure out the bigger number among the x and not x in its connected component. So among indices I plus k, I plus 2k, and so on. But also I keep track of by how much the answer drops if I decide to flip my decision. So maybe this will be This will know information that by default I increased the answer by 30, but there is a possibility to use 0 here instead of 1, and then the answer will be 25. Then second position, maybe here by default the answer is 28, and I can do -1 if I flip, and so on. So if I flip this 0 into 1, then it flips all the other yellow positions, and then I will have 27 ones instead of 28. Then I need to look at the parity of this. So again, at each of those k positions, I chose the option x is 1 or 0 that gives me more ones in total. And then if the parity doesn't match the required parity of the first range, I need to do one of those flips, the one where I lose the least. So the drop closest to 0. So let's work with positive values. Here the answer drops by 5, by 1, and so on. Choose the minimum of them. And by that much decrease the answer. That's the end of the solution. So summary, so that we would know from the beginning what we're doing. When you compare the first range to the second range, the information whether their sums modulo 2 is the same or not gives you information whether the first bit and the bit at position k are the same or not. Always comparing two consecutive ranges, you get information about the interaction of indices I versus I plus k. This gives you connected components. For each of k initial indices, you can keep jumping to the right by plus k, and you will know comparison if new bit is the same or different than previous one. By pretending that the first such bit is x, this is the bit among the first k bits, you can express all the others in its connected component as x or not x, count both, and let's say to solve the maximization of the number of ones, we choose the maximum of the two values. And it would be great if the answer was just the sum among the first k bits, the sum of the better option, the one maximizing the number of ones in the string. But we also see what value of x, 0 or 1, leads to this bigger value. And we put the value that puts us there, we put it here on the corresponding index. So similarly, we'll put something here, something there. And you check, once you put it on the first k slots, we check if the sum of the first range is even or odd, correctly, whether this information matches what was given in the input. If not, then one of those bigger numbers, like 30 is bigger than 25, we need to change into the smaller number so that the parity would change. And only a single change is enough. So among all the possible drops, like from 30 to 25, there is a drop of 5. We choose the smallest drop, and we decrease the answer by that much. That's how we maximize the number of ones. Minimizing number of ones is same, but we take minima and we increase the answer instead of decreasing. Everything here is linear, so time complexity of n. No, you at some point take minimum of some values. You don't need sorting for that. It's just iteration to find minimum. And that's, I think, the last problem. Time for questions if you have some. And reminder that tomorrow, same time, we will have gold and then platinum. The goal is to do it in 1 hour each. We'll see how that goes. So yeah, gold will be the first hour, and after 1 hour, we will start platinum.
Yes, friendly reminder, because this is ASCAP the first time to host a platinum level solution. So welcome students to join us and learn more from the experienced competitor and Coach Camille.
Yep. I will see how the Platinum goes. It's always hard to discuss difficult problems before the official editorial, because there is always a high risk of skipping some solution because I don't know about it, and smaller chance of just making mistakes. But it happens. We'll see how it goes.
Okay,
Uh,
I think no more question from the YouTube as well.
Great. Then thank you everybody for attending today. And yeah, for example, in the Discord USACO unofficial server, you can find the statements if you want to read gold and platinum problems before tomorrow. So thank you everybody. Have a good day or a good night, and see you tomorrow, same time.
Thanks. Bye, everyone.
Bye. Okay, I'm heading off. See you tomorrow.
Thanks for your time. Yeah. Oh, we will collect some feedback because due to the time zone, right? Because some parents give us some feedback that the kids cannot join the live solution because the Pacific time. So maybe next time we can discuss about the time. Yeah. Thank
Sure.
you so much. Yeah. Come on,
Bye
bye.
bye.
Bye.